In this video, we're going to have a look at the Suzuki reaction. The Suzuki reaction is a very valuable palladium-catalyzed organometallic reaction where you take a vinyl or aryl boronic acid or some other boron vinyl or aryl compound, here's the boronic acid, and you couple it with a vinyl or aryl halide or a triflate. And we'll see triflates in particular are very valuable as we look at them a little bit later. Also, Suzuki was a Japanese chemist of some note, not the guy who made motorcycles, but organometallic chemist. And this is a very well-documented reaction. It's used all the time. So let's look and see how this has worked. Well, of course, the weird thing about it, you have to start off with these boron compounds, and so we have to figure out how to make a boron compound. Well, it's not too bad. You basically use hydroboration, but you do it with very special boron compounds. So here's an example. You take an alkyne, you can add this boron hydride. Now, what is that boron hydride? Well, it's secondary isoamyl. It's a very weird looking thing. It's these amyl is basically means a 5-carbon fragment. It's a specialty name for pentyl. So isoamyl is like saying isopentyl. But anyway, the key thing is it's a very sterically hindered boron hydride. So one thing it means it can only add onto this thing very specifically to the terminal position, not just because of electronic reasons, but also because of sterics. So anyway, this is a good example. Another example is this guy here, 9BBN, where you have a boron bridging this ring, which makes it again very sterically hindered. And again, this is very specifically I'll add one time. Or you can use catechol borane where it's hooked to this catechol is dihydroxyphenol, and so this is hooked to dihydroxyphenol. And again, this is a good reagent. And all three of these will add to this alkyne exactly one time to give you this trans vinyl borate. So catechol borane is a good example. It'll add to that triple bond. And then other way of making these things is that you can use Grignard reagents. If you have a Grignard, you can react it with this trimethyl borate, and you'll make a dimethyl borate. That can be hit that with some acid in water, and it'll go to the boronic acid. So all these compounds can be used to couple with the palladium. Here's an example of using a lithium reagent with a trimethyl borate. Again, they're easy. These boron compounds are pretty straightforward. The interesting thing about these boron compounds, they're very, very stable. And so these days, if you go to the chemical catalogs, you can buy a large number of these things already made to do your chemistry with. So oops, here I'm jumping around. Anyway, so let's do one of these reactions. So here's a good example. Here's this boronic acid. Here's a vinyl bromide, and you get this very specific coupling. It retains the stereochemistry in the double bond up here. It started off cis, you remain cis. You get a straightforward coupling. The boron leaves, the bromide leaves. You get a straightforward coupling of the bonds. So it's very, 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 very important reaction, very specific. And so let's look at the mechanism. Well, the catalyst is a palladium phosphine. The active species is thought to be just 2 coordinates. So that would be palladium is 0 is 10 electrons, 2 phosphines. That would be a 14 electron compound. We start with an oxidative addition. Okay. Then it was thought that the ethoxide, we're throwing in some extra ethoxide base, the ethoxide coordinates and it just displaces the bromide. And you say, well, why do you want ethoxide? Well, ethoxide, it turns out, has a special affinity for boron. And so, because boron really likes oxygens. And so boron will coordinate to the oxygen lone pair and bring that R group in vicinity of the palladium. Then there's a transmetalation step where basically that R group migrates over to the palladium and it kicks out the oxygen about kind of at the same time. And what you've done is end up doing this, what we call a transmetallation reaction, where you've moved the R group from the boron to the palladium. And now we're all set up to do a reductive elimination, which is going to be the final step. And the boron, the borate just ends up here as this anion over here. So anyway, this is a very straightforward reaction. The odd thing is this transmetallation, because this really isn't one of the standard organometallic reactions we talked about earlier. So I want to look at that a little bit more, and because it's very important in a lot of these reactions. So this is the transmetallation step. And the weird thing is how does that R get from the boron to the palladium? Because they're not bound. Well, it's thought to go through this bridged intermediate where it's kind of forming half bonds to each of the two species. Now, looks very unusual, but the amazing thing is that there are stable compounds which actually have this kind of bonding. A really good example is the very simple compound which is you would call trimethylaluminum, except trimethylaluminum is actually a dimer. There's 2 aluminums and 6 methyls. And the structure of trimethylaluminum dimer has the methyl groups bridging the 2 aluminums. Now that's really bizarre because it looks like a carbon with 5 bonds. But it turns out it's not disobeying the octet rule, because if you count up the electrons, there's only 2 electrons associated with these 2 bonds. These are delocalized sigma bonds. There's an empty aluminum orbital on each aluminum, and there's the methyl. Basically, think of it as a lone pair. Think of it as a methyl minus. That methyl minus is bridging the 2 aluminums. So the 2 electrons are in orbital delocalized over 3 atoms. Now that seems very weird, but it's not that weird. It's called a 3-center 2-electron bond. We have 3 atom centers, but only 2 electrons shared between them all. It's very much like thinking of the delocalized pi bond in the allyl cation. Here we have a pi bond, 2 electrons delocalized over 3 atoms. Well, this is really the same thing. It's just that they're sigma bonds instead of pi bonds. So this turns out to be a very common thing, and it explains a lot of these transmetallation reactions. Here, when we made our borate in the first place from a Grignard reagent, again, we had to pass the carbon from the magnesium to the boron, and again, the intermediate you would think of as this carbon bridging the 2, very much like this methyl over here in aluminum, trimethylaluminum dimer. So it's not a big mystery, but it's still pretty weird. Anyway, so let's do a real example. So here I'm going to do an HBr addition to an alkyne, and we're going to do this hydroboration reaction with this secondary isoamyl compound. So this one we just went through. We know what that gives. So what's the final product going to be? Well, pause the video and see if you can figure this out. And of course, the way I want you to figure it out, having paused the video, is first figure out the structures of X and Y. So pause. Okay, let's go. What are we going to get here? Well, X and Y. What is X going to be? Well, this is where we're adding, of course, just forming the rules that you did last semester. Proton will go to the terminal atom. The bromide will go to the second atom, and you'll end up with this vinyl bromide. Here's the hydroboration step, where the boron will do go to the end carbon. The proton will go to the second carbon. You'll get this particular compound. Now these add syn, so it means you get a trans compound. So now all you have to do is do a direct coupling between this bond and that bond, and ask yourself, which compound down here is it? Can you see it? So what you want to do is you want to look for this fragment. So this is the fragment which is going to couple on to that carbon up here. And then look for this fragment. So this is what, 1, 2, 3, 4, 5 carbons with a double bond on the end. 1, 2, 3, 4, 5 the carbons with a double bond in, so that would work. But this is a cis bond. This is trans. 1, 2, 3, 4, 5. This is the one we want B. So the answer is B. So that's not pretty hard. But you see how specific this is. It'd be difficult perhaps to make this compound from other methods. So that's a Suzuki reaction. It's really quite powerful. But one of the things that makes it even more powerful is that you can start off with ketones, because one of the things you can do to a ketone is that you can through enolate chemistry, which we're going to talk about next, actually, you can turn it into a triflate. Now, what's a triflate? A triflate is a derivative of this trifluoromethyl sulfonic acid, which is a very, very strong acid. You start with a triflate anhydride, and what happens is the pyridine pulls off a proton there, forming an enolate, which attacks this thing and forms triflate. So these things will form very easily. You'll get the thermodynamically most stable enolate, is that you could form this on either side, but it tends to form on the more stable side, the more substituted side. This is more substituted double bond. So here's the triflate, and then you can use these in the Suzuki reaction. Now it looks kind of like the like TMS, but it's not. It's not a protecting group like TMS. It's an activating group. It makes this a very reactive species. So anyway, we can do this. So we're going to form that triflate right here. So you're going to have a double bond and an OTF, and you're going to couple it with the product of hydroboration here. So do the hydroboration step here. You'll get your boron on you'll form a vinyl boron, a vinyl borate, and up here you'll have a triflate. So again, figure out what X and Y are. Stop the video and see if you can work this out. Okay, so what are we going to get? Can you figure that out? So what do we want? Well, we know the triflate is going to be a double bond OF. So we've got to have, we're going to look for one where we have the double bond near a carbon. So here's an example like this one down here. It's not going to have any oxygen in the final product. That's just a red herring. So these oxygen ones are out. The triflate is going to form a carbon-carbon bond. So which one are you going to get? Well, we have the double bond next to the bond. That's the one we want. Of course, this one here, but is it going to be cis or trans? Well, this gives trans, so it's B again. So there's our triflate. There's our borate, and whoops, and indeed it is. It's going to be B down here. So that's the Suzuki reaction. It's a very useful reaction and not that difficult to apply, and it's very useful in doing all kinds of organic synthesis.